language model. So in terms of definition, language model is something like that generates likelihood of word sequence, enabling us to identify the missing or the next token. So in this case, when we said like what is language, based on this context, it is trying to identify what the next word is. It could be model, observer, or feature, which are high likely sentences. Google is trying to do it. Of course, it's in a smaller model, but much more sophisticated language model also follow the simple exact strategy. But on a whole, but this is the overview, like a fundamental definition of language model. But right now, we will get into in detail of how this language model has been evolved over the period of time. So, yeah. The language model's evaluation can be broadly categorized into four major stages. First one is like SLM or statistical language model, which begins somewhere in 1990s. So they are meant for task plus specific use cases, like next word generation or something like this. The next stage of language modeling so here the task specificity of the language model is moved towards task agnostic feature learners. So they can be used across wide range of tasks. Then with later little bit of advancement, we came across pre-trained language model, which are some of the sophisticated language model which gives us the capability to transfer the knowledge that is learned from one task to another. So inspired from how humans learn. And with 2020, we are in the era of large language modeling, which we are seeing all around. Like some of the examples are what I have shown in the first slides, like ChatGPT, Gemini, and everything. So let's get a little bit deeper into it, like how it is. So when talking about statistical language model, so the prominent language model, prominent one which we need to address here is n-gram model. So n-grams are nothing but chunk of n consecutive tokens. So let's take the example of what we have it in the first thing. So what is the language? That is what we have given. In case if we consider it as a unigram, what it says is like just what is a language. All individual words are considered as a unigram. In case of bigrams, it means pairs of two. So one, like what is a language and everything. Consequently, trigram, fourgram and everything, like the number of words that needs to be windowed are actually getting increased. So that is exactly what I mean by n-gram. For the simplicity of the presentation, we will consider bigram for our example. So it could be, but the same concept can be extrapolated to other n-grams as well. So how this language model works is they collect statistics about how frequent different n-grams, in our case it's bigrams, are occurring and use them to predict what the next word would be. So this is completely based on Markov's assumption, which is something like predicting the next word based on the most recent occurrence of context. So let's do a little bit deeper. Mathematically, if we want to express the word which we have discussed about, so we want to say what is the probability of getting a model given the context which we have earlier is what is the language. So basically it falls in the formula of like W of n, what is the next word, given its history of what everything here it is. Since we are talking about bigram, we have the history size of 1, which essentially brings to probability of model. What given language is actually the n-gram general definition, which brings to probability of like model given language. So this is how mathematically we are representing it. But how do we actually compute it? Is again pretty simple. It's a straightaway formula. So just count. Simple counting is what we are doing it over here. So we will just compute, like we'll take a huge corpora and we'll just calculate number of times the word language and model whichever probability has the maximum value, we can able to assign. So basically, like whichever, for each word we need to compute it, and whichever has the highest probability, we can able to say this is the missing word we are looking for. So in our case, if we do the same thing, we got model. Okay, so this is something of model which we can use to predict simple words actually. But this has done something in 1990s, and they have some significant amount of problems. So the first thing is like they are extremely dependent on the training corpora because they rely heavily on probabilities of the word sequence. Let's say if a particular word is not at all occurring in a sequence in the training data, that means they get zero probability, which the model will never predict that word, which even though it is grammatically correct and a plausible sentence. So some advanced methods like smoothing can able to mitigate it a little bit, but it's still it's still a vital problem actually. Any questions? Okay. Okay. Okay.
One question, sir. Excuse me.
Yeah.
Sir, this language model only we concentrate about English language model. Otherwise, regional language also is same only.
Sorry, I didn't get it. Can you please reiterate it?
Language model we are considering only English language, English language only, or regional language also same thing only.
Everything is same. Like language is kinda like depends on the training. Like conceptually, everything is. This is going to be similar for whichever language you're training. It could be English, German, French, whatever you want, you can say it. Underlying training corpora, like which you want, is like defines. Like if you're giving an English training corpora, it will be trained as an English language model. If you're giving a Tamil corpora, it will be trained for Tamil language model. So that's the thing.
Okay, sir.
So
Thank you.
yeah. Anyway, thanks for the question, by the way. So yeah. So this is not a stats data problem, and also the next thing is like the context which we are talking about. So the next thing, in the earlier case we see we are using the history of one, which means only the previous word is getting taken into context. So other words in the sentence are like actually not considered while computing the probabilities, which of course we could able to mitigate it if we are using a larger engram, but it also increases the data sparsity problem if we increase the engram size, and it can able to result like in suboptimal models. And also the third problem is like these are like highly relied, as I mentioned, like it is highly relied on probability computation. If the number of words in a vocabulary is extremely large, the number of probability computation you need to do is also drastically increases, which makes it computationally complex. So these are some of the fundamental problems which we have with statistical language modeling. So at later point in early 2010, so this researcher like neural networks were slowly gaining attention, and people started to see how can we model the language in using this neural network. So that gives rise to, of course, neural networks able to learn any meaningful representation from it. Or else it could also, that is a major problem, so it could lead to unstable training. The second one is the long-term dependency problem. So let's say if you say like clouds are in there, and if you are asking it to predict, we can say sky. So we know of course clouds are in the sky, and we can able to make it like what we are asking is like it is related to a subject cloud. But let's say we are talking about something like this, clouds are in the sky, and I am talking about 5 to 6 sentences, and then say the color of it is, and I am asking it in the sense, here I refer say it towards the cloud, and I need to get the answer blue. Of course, as a human we can able to process it, but this language model with limited capabilities, with addition of new information, they may lose the information that is already holding in the context, which essentially make them to give inaccurate information, because the crucial information which is essential to derive this output is already lost from the memory. So that is something like known as long-term dependency problem. So these two problems are like a major thing that exists in a recurrent neural network. LSTMs are like a variation of recurrent neural networks that is specifically developed to address the long-term dependency problem, and also it mitigates the vanishing variant problem to a great extent. So that we will get like slightly look into in a little detail. So LSTM stands for long short-term memory. So through this approach gets prominent attention in 2013. The approach was initially proposed in 1995. So as a technical report, but it got published in 1997 itself in conferences. So this works like that, but it slowly gets attention once we have like started to explore it in a neural network perspective. So fundamentally, this recurrent neural networks are like a chain of RNN cells or like LSTM cells that are grouped together that process each sequence at a time. So I can able to. Okay. So basically here we have 3 gates in the network. They are circuit gate, input gate, and output gate. So okay. So basically like these are the 3 gates.
ஒரு FTP அது இந்த chips உடனே இது பண்ணாங்க கேட்டிருக்கான் கொஸ்டின்ஸ்.
Madam, please unmute your mic.
ஆமா, அதான் எப்படி ஆன்சர் பண்ண தெரியல, அதான் காப்பி பண்ணி மெட்டால போட்டு ஆன்சர்.
Madam, mute your mic. You have unmuted it.
நானே இன்னைக்கு ஜாயின் பண்ணதே லேட்.
Somebody is speaking about this. Please mute your mic.
It's glad to hear you are using language like Llama language model to answer the questions. Okay. So okay, we are talking about gates. So what does fundamentally a gate mean? So gate is a way to optimally let the information through. Like you can able to consider like a normal gate at your university. So you can able to let only the people with a valid ID cards or like something to get through, and other people are not allowed to do it. So same case happens with in terms of neural networks. So here like we decide which information needs to be kept or passed to the next state, or which information needs to be discarded. This is decided by the gate actually. So in terms of gate, how it operates is like it's just like a sigmoid layer which is followed by a point-wise multiplication operation. So as you might all know, sigmoid layer outputs the number between the range of 0 to 1, which essentially say updating all the cell state information from the equation which we had from the earlier state. Then finally we have the output gate, which decides what are the output information that needs to be given out as an output for each cell, and also that needs to be passed through the next hidden state. So this is like a high level overview of what LSTM functions. Okay, so yeah, there are like over the period they have also developed several variations of language models, and one of the prominent variation is again gated recurrent unit. So this came us in 2014. So they are also essentially function similarly as the LSTM model, but only difference is, so instead of like input and forget gate, they use a single gate. By this way, this is not a single gate. By this way, they can able to reduce the number of and reset gate is kind of similar to what we have as an update gate. So the reset gate determines how much information of the past information should we need to combine with the current input. With this, we can able to see a small like a illustration of how information is getting passed.
Please, audience.
சொந்தக்காரங்க மேம் சொல்லிடுவாங்க மேம். சொல்லுங்க மேம். மேமுக்கு அவங்க வைஃப் வந்துட்டு எனக்கு ஹஸ்பண்டோட ஊருக்கு வந்துட்டு
Please mute your voice, ma'am.
அப்பதான் தெரியுது.
Madam, please mute your mic. Thank you.
Okay, then let's start it again. So here is the small. So here is how sequence to sequence model is nothing but like a sequence is like it processes the sequence of input and it also generates a sequence of output. So that is like two sequences together means sequence to sequence model. And here is how machine translation sequence to sequence model works, and you can able to see how the informations are passed through. Like I'll just play once again. So first we are just having the input words. From first it goes to an encoder and we have a hidden state representation. Then the second word is taken in and we are getting a second hidden state representation, and it goes to third and we are again getting a second hidden representation. Finally it passes to a decoder, which again generates one after the other, passing the same way like the hidden information. So in terms of looking at like here, like as I said, like each input is taken in and the hidden information from this is passed to this one. So the hidden information that is reaching here also has the hidden information of the earlier state. So likewise it goes to the end of the encoder and we will get a final context vector. And this context vector is passed this context vector is used to generate the successive sequence which we are needing at the generation end. So this is the And once it is done, the same hidden state information from all the intermediate, like all the encoders are stacked together, and this attention is computed at the end, and then the decoding process starts. So that like all the hidden state informations are present together, so the generation quality could be much more increased. So these are some important findings that came out of like a neural language modeling. And apart from this, we also need to cover one important other concept known as embeddings. So in statistical terms, we can easily represent words like, okay, we can just give them a vector and we can able to say like, okay, we can able to compute them and everything. Because most of them are based on count-based metrics. But in order for the neural networks to process them, we somehow need to vectorize those words. How can we do it? There are different ways to do it. One prominent approach is like one-hot encoding or something. But the problem with those things is, in case if you are having 10,000 words in a vocabulary, your one-hot vector dimension would be also 10,000. So it's like if I am having like hello is the word, that means hello, like let's say hello is the first word, that means 1 followed by 9,999 zeros. So that is how the thing looks like. So we can able to vectorize it, but this takes up a lot of things. It gives us fast representation, it takes a lot of things. And also there is no notion of similarity inside one-hot vectors. Like we could, like let's say in simple terms, like we use hello world, which essentially we hope like it will be having like a very, very close association. So something, or else, yeah, or else like some terms like maybe like something like a university and like a TVs or something, like those words are coming in, like those things needs to be something like a separated kind of thing. But in case if you look into the representation, the vector space, if you plot all the vector representation, all the informations are at equidistance, from which we can't able to infer any meaningful semantic information from it. So basically, in order to do that, how can we do it? Is the question the people asked a while back, and they came out like, why can't we make the model to learn the vectors by themselves, which gives rise to an important framework called word-to-vec. So which is essentially for learning the word vectors. So for the case if I refer, what embeddings means is something like in a vector space, similar objects needs to be closer or needs to be placed close by, and properties with like the names of objects with distant properties needs to be placed far apart. So that is what we mean as embeddings in embedding space. But how do they achieve is like this. So two prominent approaches are continuous bag of words CBOW or else skipgram. So conceptually they are pretty simple. So for the current text, which is T, the surrounding information of like T minus 1, T minus 2 and T plus 1, T plus 2 are information are considered, and we are using a neural network to generate a vector representation. In the skipgram is an exact opposite of it. With the current word given, we are trying to identify what are the surrounding context it could be. What are the T minus 1, T minus 2, like the previous and as well as the afterwards of the current word would be. So even though they look simple, they are particularly proven to be an effective one. So this gives some data, we will have the model, and we will train the model for the task, and we will get the model available, and we can able to use for inference. From this point, the people decide instead of doing a single round of training, we can able to do a two-stage training. First one is a self-supervised retraining, followed by knowledge transfer in the fine-tuning phase. So this two-stage training is actually getting used in all the rest of the architectures which we will be talking, and all the recent architectures we are talking about again. So right now, even though like it has gone to multiple stages, more than two, but this two are something like it's very crucial to me. On the first stage, in the pre-training, the model learns about general characteristics of a language, like its semantic structure, syntactical structure, and all the relationship between languages, and the nuances of the languages are like captured in the first stage of training, which is done in an unsupervised way, which also essentially means we don't need label data available. And the second stage is essentially targeted towards aligning the model towards our end task, downstream task. So, okay, this is, okay, the version of the transformer architecture that is proposed, like, is taken from the paper, so it's just very different here. Here, though this looks complex, we'll have a simpler version in next slide, but I'll just give an overview of how it looks in the section here. So we will have an input, and followed by we will have an embedding layer, which is computes input embeddings, followed by a positional encoding, which, okay, also the second thing I missed is, so far like in the LST models which we have talked about, there we essentially maintain sequential input. We process one sentence after another. So of course the sequential information is maintained. But in later part of 2017s and 18s, the GPUs are became more popular, and the computations also get a little bit cheaper. So there is like a huge abundant availability of GPU resources. So people want to parallelize the training which they are doing it. So here transformer networks actually don't process the information sequence-wise, but at least during the training, they take all at once and they give all output at once. So since it takes all input at once, we somehow still need to incorporate the sequential information into the data. So in order to achieve that, we are having a positional encoding layer. Followed by we will have like a multi-hit self-attention to be precise. Then we have an normalization layer, and we have simple feed power layer. In the same case goes with the decoder. Only modification is like we will have a cross-attention layer, and rest remains the same. Cross-attention is for transferring the knowledge from the encoder into the decoder to align the decoding process. Exactly. So considering the example which we have taken earlier, so the input is passed to a stack of encoder layers, and from the final stack we will give the data to a decoder, and all the decoder again processed again to a stack of things, and we will get the final output. So this is again fundamentally like it's also a sequence to sequence architecture. And if you look into individual block in the encoder level, like I'm just looking into encoder, but the similar architecture also holds for decoder as well. But yeah, in terms of encoder, we have two blocks essentially. First is self-attention, and the next one is feed forward network layer. So self-attention is nothing but attention is nothing but like it's computing importance of each element in a sequence with respect to one another. Self-attention is the case it is the same, but here the source is also the same and target is also the same. Like computing the importance between each, like the same sequence with itself. So in case if you look into the left, you have some words, they are tokens, we used called as tokens. So the same tokens are given at the right side as well. At every point of time, we will have how much, like basically the strength of, like importance is highlighted at the brighter the color is, the higher the attention strength is, and lighter the color is, having something like the animal didn't cross the street because it was too tired. So we are currently having as an it. So by editing we can able to say it refers to the animal. With using an attention mechanism here we can able to say like we have the bright lines towards the animal thing. Rest of them we are having complete scope but they are like very light and which essentially we can able to have infer like meaningful semantics or like another resolution or a resolution property could be extremely well. And the exact formula of computing self-attention is given in the left side of this thing, but I'm not going to go deep into it considering the time which we are running out of. So just a small illustration of how the encoder processes the data. So first we are having input and we are having an embedding. As I said, like this is actually the positional information that gets encoded and we are getting the input and we are just giving the output like a hidden representations to the decoder and the decoder gives the first output. And from the second stage, the decoder takes hidden information and then it processes out the thing at the end. Like for every third word, it is taking the previous word as an input and what the generated word is taken as an input and it processes the next word. So in auto-regressive fashion. Okay. So far, if we have covered like 90% of the presentation slide which I want to, in a theoretical level. So let's go to the final important part. So far we have talked about like a sequence-to-sequence architecture. There are like sequence-to-sequence models that are prominent like T5, BART and everything, so which have an encoder and decoder and they can able to use for most of the natural language understanding and processing tasks. But there are also specific case of models like which has only encoder or else which has only decoder. So in this case we will be having only this encoder section of the model. If those models are like called encoder only models, one typical well-known example is BERT, Roberta, ExcelNet and everything fall in this category. And the other case of model which is decoder only models, so encoder only models are mainly towards natural language understanding tasks like classification, regression, they are very intended. For natural language generation tasks like generating a sequence of like if you want to write coherent text or something, then natural language generation models are used, for which decoder-based models usually preferred or encoder decoders can also be used. So one of the prominent example of decoder only models is GPT. So far we have talked about using pre-training. Of course, there are a few ways we could able to achieve it, but we are not going in detail. We are just having a high-level overview right now. So far, like we started with just a small summary. So we started with statistical approaches. Then we talked about like how neural networks are getting introduced into language modeling and how the like advanced architectures, like parallel architectures, like transformers are getting used. Then we have the next variation, large language model, which are like what we call it right now as LLM. So they are nothing but whatever we have talked about in the earlier case, pre-trained language model, but in a very, very huge size. So the studies have been done on the language model and we have these findings like in case if we could able to increase the number of parameters, volume of data and the amount of time that is involved in training, we could able to have much more powerful models available. So everyone started to do all these things, which resulted in massive language models. So I'll just go with a prominent one, GPT. So when the first version of GPT came out into 2018, so it only have 170 million parameter model. When the second version later in 1 year when it came out, it has almost 10 times more parameter, 1.5 billion parameters. In next year, it got increased to 175 billion, which is 100 times increase than the previous version. In 2023, GPT-4 got released, but OpenAI didn't officially release how much parameters it actually has, but the speculation says it has crossed right now everything has surpassed way ahead. So this is the small intro of what the language model and the space of NLP is. Now we will get back to its application in a medical domain. I'll just need to quickly ask if there are any questions you have or like anything. Okay. Then we will get into it. Okay. So in this case, I will talk about important problems with the chemical domain, the clinical domain, and how language model can able to assist in mitigating those problems and able to help and can able to automate a lot of stuff. So first is clinical documentation and workflow automation. So one of the major problems that exist in medical domain is taking clinical notes, taking information about how the patient is and what is the condition he is having, what are the clear conditions, everything. So all hospitals needs to maintain them, and there is not a well organized structure for taking notes, and every note can able to vary since it is taken since the person who is taking is varies from each varies across reports. So there is a note standard format, and 80 to 90% of the clinical data are comes under unstructured format, which means in order to process we might need to have we might this natural language modeling approaches can able to vary. And this, even though this is unstructured and it's time consuming to process manually, lot of crucial information can be extracted from this data. In case if someone has some symptoms that might be available on clinical notes, but that could not be since it's a long thing, sometimes it can be overlooked, and we could if a language model is doing that, it can able to identify, it can able to point this to the doctor, so that the disease could be treated at an earlier stage rather than at the later part. So this can be also helpful in this case. And again, mining actually the large amount of data can able to unlock some of the crucial characteristics that is keeping hidden, and it can able to avoid taking new tests or even able to identify symptoms without even to take some medical tests. This is something that you've been able to get it from data, and also this is also helpful in terms of physician as well. So on 2024 they have conducted a survey in which 90% of the reported doctors mentioned they are feeling burned out, and 64% cited that it's mainly due to the clerical job which we are talking about, taking all the manual notes, digital summaries, and those. And again, these are very slow and inconsistent and it's time consuming process. So for this case, if you are using a clinical assistant which can able to analyze those data from the unstructured text, and it can able to give meaningful inferences. So those solution can able to greatly help the doctors as well as the patient. And also, rather than typing or manually writing the text, we can actually use speech-to-text software automatic speech recognition software, which can able to convert interaction and automatically drafts accurate clinical notes for you. And also sometimes in case patients may have a long clerical data, maybe 10 and 20 pages might be, if we could able to have a summarization model which could able to say it can read through all the important the data, and it can able to give you exactly what you are being needed for processing further in a precise manner. That could also greatly save time, and it can able to be helpful for addressing the patient's illness. So on a clinical documentation and workflow automation level, this language model can be useful in these following ways. And secondly, they can also be greatly helpful in patient communication and engagement. So the main problem over here is not be was really easy for non-native, like again, so for like a non-doctors. Also for in case if we are like traveling and to a different countries or something, or like different states, if the languages which they are using is not aware, like we don't have, not aware of those languages, then communicating at that time would be extremely challenging. And also sometimes clinical advice are delayed on rural areas because of non-availability or insufficient availability of doctors. So for those cases as well, we can able to have kind of chatbot which can able to answer patient questions, and they can able to guide through like a simple answering of like what is the medication, when should I need to take a medication, should I before meal or after meal, or something like simple questions, not medical advices but simple assistance can be provided by them. Of course, patient translation system can able to translate complex languages to easy to understand, or even complex medical terms into easily understandable local language. And also like a voice interfaces which can able to help to have better interaction with the patients. So they can able to ask also health oriented questions, or like if you want to schedule an appointment, you can able to do it. Like this can able to reduce the human workload by great extent, and doctors can able to concentrate on patients rather than on lifting the stuff. So these tools can actually be helpful across people from all ages, for children, and like also old age people can be also greatly benefited by this. Okay. Now 20 times larger than this. So here they are talking about a person with past medical history of type 2 diabetes, hypertension and all the diseases they are giving, and here like what are the medicine they have given and everything, and also the exams they have taken and the imaging and everything is given. Like this is the past history and what the doctors have assessed about it and what they are planning to give is what they have written in the assessment plan section. So for processing this data, we are using a transformer library, which is actually a Hugging Face library, which actually provides like a wrapper around those touch models, such as electrical models, so that like, we can able to directly easily access those, like whatever the models which we are talked about, like all the language models which we are talked about, we can able to access them and we can use it. So for this is talk about for name recognition, I'm having a pipeline named NER, and we just need to specify which model we just need to do it. For that, if we go into here, we can just, this is the Hugging Face website, and here you can able to see all the models that are sitting available here. There are like, so there are around 1 million models available, so you can pick whichever that suits your case. For this biomedical part, here is the model which I have chosen, and again you can also upload the models available here as well. Like, you can also upload and like you can download anything from here. So here, this is the model I have selected, and here you can also read a detailed description of how the model is getting trained and like what are the architecture it has and everything. You can find it here. So here and just so here I have just given a model here which essentially identify 107 medical entity types, and finally I'm just asking it to identify the nodes. Then next part is like just making it look good, like just doing a little bit formatting and just making it available good. So that is what the first part of the code does. And the second part, okay, we'll just run the first part and then we use it. I'm just running it, so it takes a little bit of time to load all the models. So you can able to see the bottom. So the models are getting loaded. So basically, from the top part, we have like, they have taken the model has given all the extracted entities. So rather than going through all these things, we can able to clearly see and like we can easily identify, like even though like let's say like for medication, let's say this metformin or like something, or like all these medical names are getting used. So also like a dosage is also given, like how much each one is getting used. We have like get to know it, and also like that is also the lab values of each of the things, like we are getting to know about it, and what are the symptoms we are getting it, what is the age of the person, what is the gender, and everything we can able to get easily. So this can able to greatly simplify the time to get to know about the patient rather than going through all this long text. So this is name recognition. The next one is, okay, this is the first part of the part. The next one is summarization. So here again what we are doing is like, instead of like going through this long text, let's give
excuse me, sir.
Yeah, you can just call me Google.
Sir, for your example, actually, all the data we put to you, then what must be the output of that one, sir? Why do I see the patient, sir? Actually,
I mean, like you're talking about demo, right?
yes, sir.
Okay. So yeah, basically it's a text-to-text model, like a sequence, like text is taken as an input. Basically, all the sequence-to-sequence model
For
processing which we
example,
are talking.
you told that text and the age of the patient, just like that, you are the input.
No, basically that. No. Okay, so doctor notice something like that views entire history about the patient, like what he has been done, or like let's say he's 50 years old, like he has like all the history of all the things they have done to him for the 58 years. He basically has some diseases or something. This is actually a truncated, like for the demo purpose, I can give it.
Okay. Summary notes, sir. For that only you have to
Exactly.
give it as a